All right, today let's have a look at the third lesson of chapter 4, C4L3. Today we're going to have a look at the derivatives of logarithmic and exponential functions. Okay, first of all, let's have a look at today's learning goals. After this lesson, you are expected to understand and interpret the Euler's number E and related key concepts. Obtain the differentiation rules for logarithmic and exponential functions using the first principles definition, and use the differentiation rules for logarithmic and or exponential functions to solve related problems. Okay, so the differentiation rule for logarithmic function involves the use of Euler's number E. So first of all, let's have a look at the Euler's number E. The discovery and discussion on the Euler's number E is a very long history and is mainly accredited to three major scientists. So let's have a look. First, let's have a look at their contributions. The first person is John Napier. In around 1614 and subsequent years, he devised a computational shortcut for multiplying very large figures using the logarithm based on a constant, which is very close to the reciprocal of E. Well, although he did not realize the importance of this constant yet. So we won't talk about his contribution here. After that, Jacob Bernoulli in around 1683 and subsequent years discovered a constant which is denoted as the limit of 1 plus the reciprocal of n to the power of n as n approaches to positive infinity. The number E we know nowadays, which is actually this expression here. When he's studying the question of continuous compound interest, he also proves this constant is between 2 and 3 using the binomial theorem. Then the next scientist, Leonard Euler, in around 1731 to 1748 and subsequent years, actually gave the name of the constant as E, which means the limit of this expression as n approaches to positive infinity is denoted by E. And he also gave the exact value of E as the sum of the reciprocal of 0 factorial plus the reciprocal of 1 factorial plus the reciprocal of 2 factorial and etc. And also prove that the number E is actually a irrational number and give an approximation for E to 18 decimal places. Well, E is approximately 2.71, 2.7, 1828, 1828, 45, 90, 45, 235. So actually, it's not very difficult to remember this figure to this 18 decimals, right? Because you can treat this number as 2.7 followed by a pattern 1828, 1828, then 3 angles in isosceles right triangle 45, 90, 45, followed by 3 figures 2, 3, 5. And Ola also gave us many more discoveries regarding the number E. Okay, so next let's have a look at the detailed work by Jacob Bernoulli, which is a question of the continuous compound interest. This will help you to understand the meaning of the number E. Okay, so let's consider this question here. Assuming the simple annual interest rate is 100, that means if you save one money $1 at the beginning of this year, and at the end of this year, the bank will return $2 to you, right? This means the simple annual interest rate is 100%. Then, if compounded once a year, how many times of your initial amount of investment you can get after 1 year? So actually, this is this case here, right? If compounded only once a year, if you put $1 in the bank will return you $2 at the end of the year, right? So in general, if we let A1 denote the amount at the end of the 1 year, and let A0 denote the amount at the beginning of the 1 year, then we have the following relationship. A1 should equal A0 times 1 plus 100% raised to the power of 1, right? Which is actually 2A0. So basically, your initial investment will double at the end of 1 year if compounded only once a year, right? Okay, then let's suppose if the bank makes this rate compounded every half a year, every 1/2 year, how many times your initial amount of investment you can get after 1 year? Okay, so if compounded every half a year, that means in the first 6 months, the rate should be 100% over 2, right? Because it compounded half a year. So every year, this rate will compound once. So for the first half year, the rate is actually 100 over 2, right? For the next 6 months, the rate is also 100% over 2, right? Therefore, at the end of 1 year, your initial investment will become A0. First of all, at the end of the first 6 months, your initial investment will become A0 plus 1/2 raised to the power of 1, right? And then because it's a compounded interest, right? So at the end of the 6 months, you get your interest and you use this interest as your investment and put them into the bank again. And the interest will also yield new interest, right? So now this is your investment now for the next 6 months. Then at the end of the 1 year, your money will become this investment times 1 plus 1/2 to the power of 1, right? Therefore, at the end of the 1 year, your money will become A1 actually equals A0 times 1 plus 1/2 raised to the power of 2, which is 2.25 A0, right? Which is slightly more than the first case, right? Then we can also consider what if it's compounded every 1/3 year? How many times of your initial amount of investment you can get after 1 year? So using the same logic, it's very easy to know that A1 should equal A0 times 1 plus 1/3 raised to the power of 3, right? And this value is approximately 2.37037 A0. And if you consider if compounded every a quarter year, which is 1/4 year, how many times of your initial amount of investment you can get after 1 year? Again, similarly, the expression should be A1 equals A0 times 1 plus 1/4 to the power of 4, which is approximately 2.441406 A0. You can see that this number keeps increasing slightly each time, right? You understand? Okay, so now let's consider, assuming the simple annual interest rate is 100%. If we compound it every 1/n year, how many times of your initial amount of interest of investment you can get after 1 year? So using the same logic, we know that the times of your initial amount of investment you can get after 1 year, A1, should equal A0 times 1 plus 1 over n to the power of n, right? Which means you will get 1 plus 1 over n to the power of n times of your initial investment after 1 year. Okay, so here naturally we want to ask a question. If n approaches positive infinity, that means if it compounded continuously along a year, the interval for the compound interest is very small, right? Suppose this is 1 year. So for example, the bank is crazy and it will compound the interest for about every 1 second or every 1/10 of a second. Then this year can be divided into many small intervals here, right? If this is the case, that means if n approaches positive infinity, what is the limit of the number of times of your initial investment after 1 year? What is the limit of the times of your initial investment you can get after 1 year? Does this number has a limit? Well, actually, the scientist Bernoulli discovered that this constant. Bernoulli discovers this constant and also proved that it has a limit. This number will not grow indefinitely positively, and he proved it. He proved that this number is between 2 and 3. And Euler gives the name of this constant actually as E. So basically, the number E comes from here. E is a limit of 1 plus 1 over n raised to the power of n when n approaches to positive infinity, and gave the exact value of E as this expression here, which is the infinite series. Euler also proved that E is an irrational number and gave an approximate value for E to 18 decimal places, which is here. Okay, so the interpretation is that this means no matter how large n is or how small the interval for the compound interest is, the maximum times of the initial amount of investment we can get after 1 year following the continuous compounded growth is E. Okay, E is the limit of this growth. That is the meaning of E. You understand? Okay, so there are some other related takeaways. So for example, let's have a look at this takeaway here. Well, if the limit of 1 plus 1 over n raised to the power of n when n approaches to positive infinity is E, we can also prove that when n approaches to negative infinity, the limit of this expression is also E. You can do it like this. So for example, we can let m equals negative n. Then we know the limit of this expression as n approaches to negative infinity can be rewritten as the limit of 1 minus 1 over m raised to the power of negative m as m approaches to positive infinity, right? And then we can rewrite the expression in the parentheses to the limit as m approaches positive infinity of m minus 1 over m to the power of negative 1, then to the power of m, right? And this can be rewritten. Something to the power of negative 1 is actually the reciprocal of this expression. So you can rewrite the expression in the parentheses to m over m minus 1, right? And also, let's rewrite the numerator to m minus 1 plus 1 over m minus 1. So that becomes the limit of 1 plus 1 over m minus 1 raised to the power of m as m approaches to positive infinity. Okay, so basically when m approaches to positive infinity, this we can if this implies that m minus 1 also approaches to positive infinity, right? And the reverse process is also true. When m minus 1 approaches to positive infinity, also implies m approaches to positive infinity, right? Therefore, these two expressions are equivalent. So we can rewrite the limit here to the new limit here. Basically, we want to find the limit of this expression as m minus 1 approaches positive infinity, right? So why do we want to write it like this? Remember that the product of two functions, then find this limit, equals the limit of the first function times the limit of the second function, right? So the limit of the first function as m minus 1 approaches to positive infinity. So is this familiar? Are you familiar with this? No? Well, actually, this is the same with the limit of a number n. For example, let's use another letter here. For example, we can let k equals m minus 1, right? So this basically is k approaches to positive infinity plus of 1 plus 1 over k to the power of k, right? Well, this limit is the same with this one. So the first part is actually all number e, right? The second part is when m minus 1 approaches positive infinity, this part approaches 0, right? Plus 1 should be 1. So the limit of this expression is 1. So that gives us e times 1, which is also e, right? Therefore, we can prove that the limit of 1 plus 1 over n raised to the power of n, when n approaches to either positive or negative infinity, this limit is e. Understand? Okay, I'll give you some time to have a look at this, because later when trying to find the derivative of the logarithmic function, we need to use this expression. Okay, have you finished? Do you have any questions? Okay, if no questions, let's have a look at another takeaway from the previous discussion. Well, another takeaway is that assuming the simple annual interest is X, so now here is not 100%. Let's suppose the simple annual interest is X now, okay? X is a positive number, not necessarily 100%, right? If compounded 1/n year, how many times of your initial amount of investment you can get after 1 year? Well, the solution is A1 now should equal A0 times 1 plus x/n raised to the power of n, right? Remember last time when x is 100%, A1 equals A0 times A plus 1/n to the power of n, right? If this number now is not 100%, which means it's not 1, but x, then you need to replace your 1 here with the x here, right? That means you will get 1 plus x/n to the power of n times of your initial investment after 1 year, right? And we can also prove that the limit of 1 plus x/n to the power of n as n approaches positive infinity is, well, actually you can rewrite the limit to this form. The limit of 1 plus x/n to the power of n over x, then to the power of x, right? As n over x approaches positive infinity. Well, because x is a number, right? So n approaches positive infinity is actually equivalent to n over x approaches positive infinity. These two expressions are equivalent. Therefore, we can rewrite the expressions as n over x approaches positive infinity. You understand? Then actually, if you treat n over x as k, so that means you have a expression like the limit of k approaches positive infinity of 1 plus 1 over k to the power of k, right? Then to the power of x. So we know that when k approaches positive infinity, this expression approaches e, right? So the whole limit will approach e to the power of x. So the result is e to the power of x. So note here when x is 1, which is 100%, this expression is e to the power of 1, which is e, right? This is in accordance with our previous discussion, right? When x equals 1, here, the limit of this expression is e to the power of 1, which is actually e, right? And in this way, if x is not 1, is not 100%, then this limit is e to the power of x. Okay, this means no matter how large n is, the maximum times of your initial amount of investment we can get after 1 year, following the continuous compounded growth, is e to the power of x. So e to the power of x is your limit of the continuous compounded growth. Do you understand? Okay, so follow the previous method. We can also prove that when n approaches negative infinity, the limit of 1 plus x over n raised to the power of n is also e to the power of x. Therefore, we have the final conclusion here. When n approaches either positive or negative infinity, the limit of this expression, 1 plus x over n to the power of n, equals e to the power of x. E to the power of x is the limit of your continuous growth. Do you have any questions? Okay, you should write this formula down onto your notebook. Okay, I'll give you some time to have a look at this. Okay, any questions, just let me know. Okay, then let's have a look at the third takeaway from the previous discussion. Well, actually, the continuous growth model can also be used to describe other similar problems as well. For example, assuming the simple growth rate, which means without considering the compounded effect after 1 unit time. 1 unit time could be either a year, a month, a day, an hour, depending on the context of this problem, right? Assuming the simple growth rate is x, where x is greater than 0. For instance, one cell becomes 1 plus x cells after 1 unit time, without the compounded effect. If the growth occurs continuously, That is, the growth occurs every 1/n, every 1/nth of the unit time, and n approaches positive infinity. Then, considering the compounded effect, the number of times of the initial amount after 1 unit time is given by this limit, which is the limit as n approaches positive infinity of the expression 1 plus x over n to the power of n. And this limit equals this limit equals e to the power of x. Specifically, if x equals 1, then this limit equals e to the power of 1, which is actually e, right? For instance, one cell becomes e to the power of x cells after 1 unit time with the continuous compounded effect. Understand? Okay, so these are the major takeaways from the discussion of this problem. Okay, so this problem is called continuous compound interest. Okay, again, I'll give you some time to have a look at this lecture slide, and after that, we'll try to derive the derivative of the logarithmic function. So here, note that we haven't touched the derivative of the logarithmic function yet, right? All of the work done here is in preparation for the differentiation rules for logarithmic functions, which we'll be discussing later. Okay, so first of all, have a look at this lecture slide. Okay, do you have any questions? If not, let's have a look at the derivative of the logarithmic function now. So here we are going to find the differentiation rules for logarithmic function first. Okay, so we consider a logarithmic function f(x) equals log base a of x. Of course, a is greater than 0, a cannot be 1, and x is greater than 0, right? That's the domain of the logarithmic function. X is greater than 1. X is greater than 0. Okay, so the derivative of f(x), according to the definition of derivative, is the limit of f(x) plus h minus f(x) over h as h approaches 0, right? Then let's substitute the expression of f(x). Then that gives us the limit of log base a of x plus h minus log base a of x over h as h approaches 0, right? So note here, we can put h in front, and using the power rule for logarithm to put 1 over h here. Okay. Can you follow me? And also, the difference rule for logarithmic tells us the difference between two logarithms is actually the logarithm of the fraction of these two expressions, right? Therefore, log base a of x plus h minus log base a of x actually equals log base a of x plus h over x, right? Okay, so we get this expression here. Well, this expression looks similar to this one here, right? Which we have already proved. Oh, sorry, my mistake. So this expression is similar to this one. The limit of here 1 plus 1 over n to the power of n as n approaches 0, right? They look very similar now. Sorry, 1n approaches either positive or negative infinity, right? The difference is that we have h approaches 0, not positive or negative infinity here. So here we can let n equals 1 over h, right? Then we have h is actually the reciprocal of n. So h approaches 0 is actually equivalent to n approaches either positive or negative infinity, right? Can you see that? Also, we know fx equals log base n, log base a of x is continuous everywhere in the domain. Then the equation number 1 here is actually written as the limit of, so note here, h is 1 over n, right? H approaches 0 is equivalent to n approaches either positive or negative infinity. So that expression can be rewritten as the limit as n approaches either positive or negative infinity of the expression log base a of 1 plus h over x is actually 1 over x over n, right? To the power of 1 over h is actually n. So that can be rewritten as log base a. We can change the order of the limit and logarithm, right? We have learned this rule before in our very first chapter. The limit of f of g of x as x approaches c equals f of the limit of gx as x approaches c. If f is continuous at limit of gx as x approaches c, we can change the order of the function sign. We can change the order of the function symbol and the limit symbol, right? So we can find the limit first, then find the logarithm based on a. Okay, so we now can find this limit first. This limit is actually e to the power of 1 over x, right? Remember that we have proved the limit of 1 plus something, let's call, for example, r. 1 plus r over n to the power of n as n approaches either to negative infinity or positive infinity. This should equal e to the power of r, right? We have already proved this. So now here the r is 1 over x. So this limit should equal e to the power of 1 over x, right? Okay, so this gives us, this is actually log base a of e to the power of 1 over x, which we can put 1 over x in front, according to the power rule of logarithm. So that equals 1 over x times log base a, log base e of based on a. So that gives us, we can change the base of this logarithm using the Euler number e, right? So that gives us 1 over x times log base e of e, log base e of a, right? Log base e of e is 1, so that final solution is 1 over x times log base e of a, right? So this is our final solution. If we have a function f(x) equals log base a of x, then the derivative of that function should equal 1 over x times log base e of a. Understand? So from now on, you can use this formula to find the derivative of logarithmic function here. Also, a special case is that when a equals e, that becomes line x, right? The derivative of line x is x times line e of e, which is actually 1. Therefore, the derivative of line x equals 1 over x. Okay, you should put these two formulas down onto your notebook. Okay, so basically this is how we can get the derivative of the logarithmic function. And we say these two formulas are the differentiation rules for logarithmic functions. Okay, I'll give you some time to have a look at this lecture slide here. All right, if you don't have any questions, let's use this differentiation rules to do a example question. Okay, so consider these 3 questions here. Can you find the derivative of each function below? I'll give you 3 minutes, 1 for each question. Okay, after that, we'll have a look at the solution together. Okay, have you finished? Let's have a look at the solution. So note that each of the functions here is a composite function, right? So please do not forget to use the chain rule. Okay, first function f(x) equals line, which is a log based on e, right? Line 4x cubed plus x. The other function is line u, right? So first of all, the derivative of line u is the reciprocal of u, then times the derivative of the inner function, right? So that gives us the derivative of the outer function is 1 over 4x cubed plus x times the derivative of the inner function, which is derivative of a polynomial function, which is 12x squared plus 1. So the final solution is here. Any questions? Okay, next question, log base 10. Note that if the base number is not specified, this is by default log base 10, right? So if this outer function is log base 10 of u, the inner function is secant x, which is a trigonometric function. Secant is the reciprocal of sine, right? Okay, so that equals, first of all, we can there's this reciprocal of secant is cosine. First of all, we can simplify that function to negative log base 10 of cosine x, right? Then that equals the derivative of the outer function, which is log base 10, right? Which is 1 over cosine x times log base 10. Then times the derivative of the inner function, which is cosine x, whose derivative is negative sine x. Therefore, the final solution is sine x over cosine x over line 10, which can also be simplified to tangent x over line 10. Do you have any questions? Okay, if no questions, let's have a look at the next one. Next one has 3 layers, right? Outmost function is a log base 7. So the derivative of the outmost function is the reciprocal of this expression times line 7 is the denominator, right? And numerator is 1 here, times the derivative of the next layer, which is actually u squared, right? So that equals 2u. So that's 2 times 2x cubed plus 1, then times the derivative of the innermost function, which is 6x squared, right? Then after simplification, the final solution should be 12x squared times 2x cubed plus 1 times line 7, this one here. Okay, any questions? Make sure you are able to solve each of the questions here, okay? All right, if you finished, let's consider the derivative of the exponential function. So note here, we have already find the derivative of the logarithmic function like this, right? So next, let's consider the derivative of the function that has this form, y equals a to the power of x, right? Where a is greater than 0 and a is not 1. So this is called exponential function, which is actually the inverse of the logarithmic function, right? So in order to derive the derivative of the exponential function, of course, you can start from the very beginning using the definition of the derivatives, right? You can try to do that after this class. Or you can also use the property of the inverse of a function, right? So now in this class, I'm going to use the second method to obtain the derivative for the exponential function here. So first of all, let's have a look at the derivatives of the inverse functions in general. Okay, now let's have a look at the derivatives of inverse functions. Note that exponential functions and logarithmic functions are the inverse of each other, right? Therefore, in order to obtain the derivatives of the exponential functions, let's consider the derivative of the inverse of a given function in general. So in general, given a function fx which is differentiable and the inverse of fx is also a function denoted by this symbol here, the inverse of fx. Or we can use another letter, for example, gx, to denote the inverse of the function fx to facilitate our discussion later, okay? Then we know that f of g of x equals x. So why is that? Because first, let's consider this relationship. Suppose we have a point x and there's an effect of g. G maps x to gx, right? Because f is the inverse of g, or g is the inverse of f. So their effects are inverse of each other, right? So, and there's the effect of the function f. Gx can be mapped to x back, right? So f of g of x is actually 0. So that means f can map gx back to x, right? Therefore, we have this relationship. Okay, because we have this relationship, then we can use the implicit differentiation rules to differentiate both sides with respect to x. Then this gives us, so note that the left side is a composite function, right? The differentiation, the derivative of that function is first the derivative of the outer function with respect to the independent variable gx times the derivative of the inner function gx with respect to x, which is actually the derivative of gx, right? The right side is the derivative of x, which is apparently 1, right? Remember that we want to find the derivative of gx, right? So the derivative of gx is 1 over the derivative of f with respect to gx, right? So we can use this conclusion to help us to find the derivative of the inverse of the logarithmic function, which is actually the corresponding exponential function, right? Okay, so I'll give you some time to have a look at this lecture slide and do write this down onto your notebook, because we're going to use it to derive the derivative of the exponential function. Okay, if you finish, let's now have a look at the derivatives of exponential functions. First of all, let's give it a recap of what we have got here. So note that we have already proved that the derivative of gx equals 1 over the derivative of f with respect to gx, right? Note here gx and fx are inverse of each other here. And on the other hand, we have also found the derivative of a logarithmic function like this, log base a of x. The derivative of this logarithmic function is 1 over x times line a, right? X is your independent variable here. Okay, so we know that exponential functions and logarithmic functions are the inverse of each other. So we can use this knowledge to help us to find the derivative of the exponential functions. Therefore, we have the following conclusion. Given a logarithmic function, fx equals log base a of x, of course a is greater than 0 and a is not 1, right? The inverse of that function is, for example, denoted by gx equals a to the power of x. Fx and gx are inverse of each other here, right? Then, according to what we have got here, the derivative of gx can be given by the reciprocal of the derivative of f with respect to gx, which means in this case that is 1 over gx times line a, right? Because the derivative of fx with respect to x for this function is 1 over x times line a, right? X is your independent variable. Therefore, the derivative of fx with respect to gx is simply to replace the independent variable x here to gx, right? Therefore, that is actually 1 over gx times line a, right? Can you see that? So this part is this part here. Then, what is gx? Gx is the expression of gx, which is simply a to the power of x. So substitute that to a to the power of x, and that gives us a to the power of x times line a, right? Line a is log base e of a. Therefore, we have the derivative of g with respect to x equals a raised to the power of x times line a, which means the derivative of the exponential function a to the power of x equals a to the power of x times line a. Specifically, when the base number a equals e, that gives us the derivative of ex equals ex times line e. Line e is 1, right? Therefore, that gives us the derivative of e to the power of x is itself, which is also e to the power of x, right? Okay, have a look at this lecture slide. Do you have any questions? Okay, so next, let's have a look at the derivatives of the inverse functions. Note that the exponential functions and logarithmic functions are the inverse of each other. Therefore, in order to obtain the derivatives of the exponential functions, we can consider the derivative of the inverse of a given function first in general. So in general, given a function fx, which is differentiable, suppose it's differentiable, and the inverse of fx is also a function denoted by f inverse of x, right? Or you can use another letter, gx. Gx, or the inverse of fx, is the inverse of fx, okay? Then we know that according to the definition of the inverse of a function, we know that f of g of x should equal x, right? Because initially, suppose this is x, and under the effect of function f, the image of x is actually fx, right? And if we define the inverse of this function as gx, so under the effect of g can map fx to the original value x, right? Therefore, we have this expression here. So g of fx equals x. And also, similarly, we have this relationship, f of gx equals x. Why is that? Because we can just change the letters. So for example, this is our x. This is the effect of g, right? G maps x to gx. Therefore, f is the inverse effect, right? F can map gx back to x, right? Therefore, we have this relationship as well. So f of g of x equals x. Then we can use implicit differentiation rules. We can differentiate both sides with respect to x. This will give us, so the left side is a composite function. That equals the derivative of f with respect to gx first, then times the derivative of the inner function with respect to x, right? So that gives us this expression here. Then the right side gives us dx by dx. Of course, this is 1, right? So remember that we want to find the derivative of the inverse of the function, which is the derivative of gx, right? We can simply divide both sides using the derivative of f with respect to gx. Therefore, we have the derivative of the inverse of fx, which is g prime x, equals 1 over the derivative of f with respect to gx. Therefore, we have this relationship, right? Please write this down onto your notebook, because later in our next discussion, we'll use this formula to find the derivative of the exponential function. Or you can also express that relationship to this one. The only difference here is the symbol we use, okay? Because gx is just the reverse of fx. You can also use the reverse of fx. The derivative of the reverse of fx equals 1 over the derivative of f with respect to gx, okay? Okay, I'll give you 1 minute to have a look at this. And we're going to use this to find the derivative of the exponential function. Okay, if you finish, let's have a look at the derivatives of exponential functions. Okay, so first let's note that we have already proved these two things, right? The derivative of a logarithmic function log base a of x equals 1 over x times line a, right? On the other hand, we have also proved the derivative of a inverse of a function equals the derivative of the inverse of the function. Well, here f negative 1, f are inverse with each other, right? So the derivative of the inverse function equals the original function of gx. This new function is reciprocal, right? We can use this conclusion here to find the derivatives of the exponential functions. Because exponential functions and logarithmic functions are the inverse of each other, right? Therefore, we have the following conclusion. Given an exponential function, fx equals a to the power of x. So note that the reverse of this function is actually log base a of x, right? Okay, then we can use this expression here. The derivative of fx, which is here, right, equals, note that f is an inverse of f negative 1, right? So that equals the inverse of that function at gx. So that is 1 over a to the power of x times line a. Can you see that? Because the inverse of fx is this one, right? And we know that the derivative of this function at gx. So what is gx here? Gx is the inverse of fx, right? So that gives us 1 divided by the reciprocal of a to the power of x times line a. So this gives us x to the power of x times line a, right? Therefore, we have the following differentiation rules. The derivative of the exponential function a to the power of x equals a to the power of x times line a. Specifically, when a equals the Euler number e, this gives us the derivative of e to the power of x is itself, which is also e to the power of x. Any questions? So here you should note that gx and fx are inverse of each other. Or sometimes you can also write the left side as the reciprocal, derivative of gx. Okay, this is better understandable, I think. Okay, let me modify this a little bit to help you better understand. Well, probably, first of all, it's better to not use this. So let's delete this first. Okay, just remember this formula here. Okay, this formula is easier to understand. Suppose you have two functions, fx and gx, then the derivative of gx equals the derivative of fx at the independent variable equals gx. Then find its reciprocal, right? So here, again, let's use gx here. Okay, then let's modify this a little bit. Okay, given on, let's say the original function is logarithmic function, right? Because we have already know the derivative of a logarithmic function. So given a logarithmic function, fx equals log base a of x. So this is our fx, right? And the inverse of that function is, let's call that gx. So gx is, we know the inverse of that function is a to the power of x, right? Of course, there are some limitations for the parameter a. A is greater than 0. A is not 1. Okay, this should be x. Okay, so according to the conclusion here, we have the following conclusion. So we can find, so note here, the derivative of gx should equal the derivative of fx when the independent variable is gx. So that is, first of all, the derivative of fx is 1 over x times line a, right? X is your independent variable. However, here, as you can see here, the independent variable is not x, but instead you should put gx as your independent variable, right? So that gives us well, do not use x here, but use gx times line a, right? And now what is gx? Gx is a to the power of x, right? Okay. This should be a fraction. 1 over x times line A, but x here is gx, right? So x times line A. And then let's substitute. What is your gx here? Gx is a to the power of x, right? So a to the power of x times line A. Then find its reciprocal, right? So that gives us 1 over x to the a to the power of x times line A. This gives us a to the power of x times line A. Can you see that? That means the derivative of gx, which means the derivative of this function, a to the power of x, equals the right side, a to the power of x times line A. And a special case is when a equals Euler number e, that gives us e to the power of x prime, which means derivative of e to the power of x should equal e to the power of x itself, right? Now, is it more understandable? Is it more understandable now? Okay, let's use enlarge this a little bit. Okay. Okay, have a look at this lecture slides. This is actually the process of how we can get the derivative or the differentiation rules for exponential functions. Any questions, just let me know, okay? All right, any questions? Okay, good. If no questions, let's have a look at some example, okay? You can use the differentiation rules for logarithmic and exponential functions to solve the following practices. Okay, I'll give you 5 minutes to have a look at these questions. Find the derivative of each function below. Okay, have you finished? Let's have a look at the solution together, okay? First question is a product of two expressions, so we can use a product rule. So that equals the derivative of the first function times the second function plus the first function times the derivative of the second function, right? So the final solution is ex times x plus 1. Second one is also a composite function, right? So that equals the derivative of the outer function, which is e to the power of u, which is itself, right? Times the derivative of the inner function, which is 2. So the final solution is 2 times e to the power of 2x plus 1. The next one can use a rule of sum. So that equals the derivative of the first function minus the derivative of the second function, which gives us e to the power of x plus e to the power of negative x. Next, again, we have a product of two expressions that equals the derivative of the first function times the second function plus the first function times the derivative of the second function, right? It is 2x, 2e to the x times cosine x plus 2e to the x times negative sine x. Then that gives us 2e to the x times cosine x minus sine x. Okay, last one is also a product two expressions. Again, we can use the product rule. The final solution is x times 10 to the power of x times x times line 10 plus 2. Okay, any questions? Okay, good. If no questions, let's consider another example. Find the equation of the line tangent to the curve y equals 2e to the power of x at x equals line 3. Express the equation of this line using slope-intercept form. Okay, I'll give you 3 minutes to have a look at this question here. Okay, you should have finished now. So in order to find the equation of the line tangent to the curve at some point, first of all, we can find the slope of the tangent line at any x values, right? That means to differentiate this function. Okay, first find slope of the tangent line at any x value by finding its first derivative dy by dx. This is a slope of the tangent line at any x value, right? Which gives us 2 times e to the power of x. Then we know when x equals line 3, then we can find the image at this point and derivative at this point. So the image of this point is y equals 6, and the derivative at this point is dy by dx equals 6, right? Therefore, we get both the tangent point and the slope of the tangent line at x equals line 3, right? Therefore, we know the equation of this line at this point is y minus 6 equals 6 times x minus line 3. This is called the point slope form, right? Then we can convert that to the slope intercept form, which gives us y equals 6x plus 6 minus 6 times line 3. Okay, any questions here? Okay, if not, let's have a look at the last example of today's lesson. Okay, now consider this question here. Okay, now let's have a look at the solution together. So in order to find its local maximum and local minimum, we need to analyze its first derivative first, right? And from there are actually two methods to find its local extrema. First, when we find the values where the first derivative is 0, then we can either analyze the signs of the first derivative before and after that point in the vicinity of that point, right? Otherwise, you can use the second method, which is to check its second derivative, right? Remember that when first derivative equals 0 and second derivative is less than 0, then it's a local maximum point. When the first derivative is 0 and second derivative is greater than 0, then it's a local minimum, right? So in this question, let's use the first method, that is to find its first derivative. Then let first derivative be 0. Then analyze the sign of the first derivative before and after that point in the vicinity of that point. Okay, first of all, the first derivative of that function equals 2x times e to the power of x plus x squared times e to the power of x. Then we let the first derivative be 0, then that gives us e to the power of x times 2x plus x squared equals 0, right? We know that e to the power of x is always greater than 0. So that leaves us 2x plus x squared must be 0. So the solution is x is either 0 or x is -2, right? Then let's analyze, if we let the first derivative be positive, then what is the solution? The solution is the product of x and 2 plus x must be greater than 0. This leaves us x is either smaller than -2 or greater than 0, right? Similarly, if you let the first derivative be less than 0, that gives us x is between -2 and 0, right? Then we know that at x equals 0, the first derivative is 0, right? And after that, when x is greater than 0, the first derivative is always 0. So this function will act like this in the vicinity of this point, right? And before that point, the first derivative is always less than 0. So in the vicinity of x equals 0, this function always has a negative first derivative. Therefore, x equals 0 is a local minimum, right? When x is 0, f0 is 0. So 0, 0 is a local minimum. On the other hand, we know that when x equals -2, the first derivative is 0. And then in the vicinity of this point, when x is smaller than -2, the first derivative is always greater than 0. So this function acts like this in the vicinity of this point and before that point. After that point, when x is greater than -2, which is here, the first derivative is always smaller than 0 in the vicinity of this point, right? So it will act like this. Oh, sorry. This should be drawn like when it's before -2, it's positive, so it will act like this way, right? And after that, the first derivative is smaller than 0, which act like this. So that point is a local maximum. And when x equals -2, fx equals 4 over e to the power of 2, right? So that point is -2, 4 over e to the power of x is a local maximum like this. You understand? Of course, like I said, you can also check the local extrema by checking both the first and second derivative. Okay, any questions? All right, if not, let's give it a summary and end today's class. So let's revisit today's learning goals. So after this lesson, now you should be able to understand and interpret the Euler's number E and related key concepts. Especially E is given by this limit, right? The limit of a expression as n approaches either positive or negative 0, or a positive or negative infinity of this expression, right? This is Euler's number. And actually, we use this expression to help us to find the differentiation rules for logarithmic function first. And then we studied the relationship of the first derivative of the inverse functions. Then use that conclusion to find the derivative of the exponential function, right? And also we looked at some questions that related to the differentiation rules for logarithmic and exponential functions. So make sure you are able to solve each of the example questions here, okay? If you want to review these lecture slides, you can check the Google Classroom and my YouTube channel after this class, okay? So please make good use of the whole of the time to review all the materials we have learned. And remember to complete and submit all the homework to Google Classroom, okay? If you have missed some of the homework before, please use this time to make them up, okay? I wish you a very Merry Christmas and Happy New Year. Okay, bye. Class dismissed. See you next year.